Welcome to Q&A for week 4. Today we'll be going over the multiple choice questions on quiz 4. And then we have some questions from the exam wrapper that was posted. And several people have given me that single Excel spreadsheet, and I was able to give them their 5 bonus points on exam 2. So let's go over the multiple choice questions. So this compound here, so this is on sapling, and the question was, what's the classification of the hydrogen atom or that carbon in the following structure? So the question you ask is, how many carbons is this carbon attached? As you can see, it's 1, 2, 3. So that makes it a tertiary. Now I would go on to say that this is benzylic, because this is a benzylic position and this is a benzylic position. So that would actually be, if you wanted to really classify it, it is a benzylic tertiary carbon. But that wasn't one of your choices. Tertiary is your choice. All right. Now the next question was, what is the starting material for the following reaction? We have NBS, bromine, HNu, and then it gives you your product. Now, this is free radical halogenation reaction. And so you can see a free radical is anytime you have like bromine and light, because the initiation step, which we have half arrows, right? Electron flow arrows, because it's one electron. And this produces the bromine radical. That's not a cation, folks. That's a radical. So that's the first thing that happens. NBS is N-bromosuccimide, and N-bromosuccimide is this compound here, and it's a source of just a little bit of bromine. So it keeps the bromine radical down low, and it's great for allylic bromination. So this is an allylic. This is allylic. So you can see that you have these carbon-carbon double bonds, and then we got the carbon here. So how do you spot it? It's an sp2, 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 and then you have your carbon bromine. So that's an allylic halide is your product. And you'll see in chapter 8 the reason why you want to keep your bromine concentration low, the bromine radical, so you don't compete with electrophilic substitution on that alkene. All right, so that's your initiation step. Well, what's your starting material? What's your functional group starting material for free radical halogenation? It's just an alkane. So the reaction is just an alkane. So here we have our hydrogens. You always want to draw in the bonds. And so propagation step 1, you react this with the radical. And so the electrons will abstract a hydrogen. So this becomes, we put HBr plus that free radical. And then propagation step 2, you want to take that same free radical. This is the mechanism I'm drawing for you. So you want to take that free radical Make sure you draw the structure properly. And then you want to generate a new free radical so it propagates, keeps going. Notice on my propagation steps I have 3 fishhook half electron flow arrows. So some people lost points on that. Okay, and then we have to generate a new radical. So that is your starting material is this compound right here. And you see that as one of your options. Reaction intermediate. Okay, so your reaction intermediate for this one. Once again, your initiation step, the bromine is going to generate the bromine radical. You'll get 2 of these. And then 1 bromine radical in your propagation step. The bromine is selective, so it will take the tertiary hydrogen. The abstraction energy is less. And we have 3 fishhook arrows here. Now we're going to lose stereochemistry here, folks. Okay? We don't have dashes and wedges because the radical, this free radical is an sp2 carbon. And so that means it's flat and it doesn't have a wedge coming at you. So you see that that right there is your organic carbon free radical intermediate from that reaction. Like I say, most of the time you want to work these problems as on a blank sheet of paper as if they're an open response, and then you want to answer your questions on the multiple choice. Okay, the next one, what is the major organic product in the following reaction? And it is this reaction. So we're already halfway there. Okay? So it's another reason why you want to work these on a separate piece of paper. So now, in propagation step 2, this free radical is going to generate another free radical. And so we got 3 electron flow arrows that are the fish hook. And then the bromine adds there to the tertiary carbon, and we generate another bromine radical. And so you can see that this here is your product. And so when you look at your different selections, this is going to be your major organic product. The bromination reactions are selective, and the reason why they're selective is because that propagation step 1 here is an endothermic reaction. Now, then it says what is the overall bond dissociation energy for this reaction. So I'll show you how to do that. So first of all, you have to write out your propagation steps. So as you see here, we have propagation step 1 and propagation step 2. And then what you want to do, and this is what I want to see in your open response. So if you do this again, which you will probably on Thursday, bonds broken, I want them listed, okay? So this is on the reactant side. And when it breaks bonds, it's going to take a positive delta H. And then we're going to do bonds formed. This is on your product side. And those are going to be negative. So you could list them negative or you could just subtract it, okay? So those are going to be a negative because they're exothermic when bonds are formed. Okay, so we'll do the yellow is bonds broken. So we have this bond broken and we have this bond broken. So then we can list them here. we have a tertiary carbon hydrogen broken, and we have a bromine bromine broken. And then if we wanted to do bonds formed, then the bonds formed are on the product side, and we formed an HBr and also a tertiary Br. So we have formed a HBr and we formed a tertiary carbon bromine. Now I get my delta H sheet that is listed in our book and also in our slides, and I look for my tertiary CH bond, and I see that's 403. 403 kilojoules per mole. I see bromine bromine is 190. Doesn't take much to do a homolytic cleavage on that. HBr is 366 kilojoules per mole, and then the tertiary carbon bromine is 304 kilojoules per mole. Now on your quiz you had to actually type in the answer here, and let's add these up and see. So 39593 kilojoules per mole minus, okay, so here's our minus. See the minus here? So we're going to minus that. And this is 670 kilojoules per mole. So you can see that you're going to have a negative, and that should be, let's see, 77 kilojoules per mole. Okay, so that is the answer. And you see how those all built upon each other on that quiz. All right, so that is quiz 4. The other objective for Q&A was answering some questions, and then also I want to bring some stuff together. Okay, so let's go to our substitution reactions. So we got an SN2 and an SN1. And so you've been working through your POGIL exercises 9A and 9B. And so I want to talk about this a little bit here. Okay, so you need to be able to identify your nucleophile, your electrophile, your leaving group. You need to be able to determine whether this is going to be an SN2 reaction or an SN1. And then you need to be able to draw the mechanism. So your nucleophile, does it matter? For an SN1, let's see if we can, let's do SN1 versus an SN2. Okay, so your nucleophile, you need a weak nucleophile for an SN1. So you want something like CH3, like methanol, or water. Okay, how do you know that something's a weak nucleophile? There's no negative charge. Okay, there's no negative charge. Now for an SN2, you want a strong nucleophile. So you want to classify your nucleophile. If you see CO3 sodium, folks, that's a negative. Sodium hydroxide, that is a negative, that's a negative oxygen. We saw some stuff like this. Okay, that gives a negative sulfur. Those are strong nucleophiles. You have pages in your book and charts and in your PowerPoints that talk about whether something's a weak or strong nucleophile. Okay, your electrophile. For an SN1, your preference is tertiary, folks. Okay, so your electrophile looks like something like this. And that carbon bonded to bromine is bonded to 3 carbons. That's tertiary. Secondary can also go, but It is the gray area. Okay, that's the gray area. And here, when you have methyl um, and primary, these are going to be really hot SN2. You get into secondary, and it's the gray area. Okay, so the gray area for SN1, SN2. And then how am I figuring out whether it's SN1 or SN2? With the gray area, well, I always, even with the nucleophile, um, I'm determining whether I have SN1 or SN2. If I see a weak nucleophile, I'm going to go with SN1. Okay, and if I have a strong nucleophile, I'm going to choose SN2. And then if I have a secondary, I mean, if I have a tertiary, I'm choosing SN1. Okay, so you can say no tertiary alkyl halides are going to go SN2. And no primary or methyl are going to go SN1. And the reason why is because it's so going to happen so fast with SN2. The leaving group, so your leaving groups, you want to have good leaving groups for all of them, right? So you got bromide leaves, iodide leaves, chloride leaves. Now I also want to talk about the tosylate, which is a great leaving group, and water. Okay, now water is a great leaving group. Why? Because it can stabilize the lone pairs that leave with it. Tosylate, great leaving group. Resonance, it can stabilize the lone pairs. Okay, so that's a tosylate. So if you see those, include those in your leaving groups. Also, another substrate you need to consider that reacts with both SN1 and SN2 that's an electrophile is the allylic, so like an allylic or a benzyl. Okay, and these are going to be fast for SN1 and SN2. So a lot of times you're looking at your nucleophile for those. Okay, so let's look at water. So you have something like this, OH. Okay, HI. Okay, HI is not a strong nucleophile. Okay, iodide is not a strong nucleophile. It's not. Oh, it is actually a strong nucleophile. Iodide is. What's going to happen here is it's a strong acid. Okay, so you have an acid. So whenever you have HBr and HCl, the first thing you have to do is look at its acidic nature. So it's going to protonate. You have to protonate OH to be a good leaving group. OH is a bad leaving group. Okay, bad leaving group, not going to leave. It will not leave. But if you protonate it now you have water, which is a great leaving group. And what happens is it's going to leave. And you get a carbocation. Okay, so now you have a carbocation and you have iodide. And then iodide can be the nucleophile. Now, this is an SN1 because we have a carbocation. You always do your carbocation test. Okay, so you want to do a carbocation test anytime you do carbocation test. So you classify. If you classify this carbocation, that carbon is bonded to, that has the carbocation is bonded to two carbons. So it's secondary. So you look at the neighbor. What if you trade places here with this red carbon? That would be a primary. Well, if you traded places here, it would be a secondary. A secondary is no better than a secondary. So it's not going to rearrange. There's no rearrangement there. But I always check my neighboring carbons anytime I make a carbocation to see if I have rearrangement before I do step 2. Now, when you do the carbocation in the SN1 mechanism, it's 2 steps, folks. So you're also going to have to match these reaction energy diagrams. Okay, So that's how you know you have two humps. Okay, this is definitely SN1 because you have a step 1 and then you have a step 2. So step 1 and a step 2 to get to your product. There's your product, there's your starting material. What's this valley? That's your carbocation. Okay, so you have a valley because you have an intermediate, and it's called a carbocation. If you do an SN2, so if you have an SN2 reaction, so let's say you have something like this. This is definitely going to be an SN2. You have a primary alkyl halide, and you have a strong nucleophile. So you're going to have an SN2, and I'm not going to make you do the transition state here, but you have this compound here, 1, 2, 3 carbons. Okay, so you have this ether. That's one step. And so that reaction coordinate looks like this. Okay, so you have your starting material, you have your transition state, which look like this, right? I will do it here. Show transition states at the peak, not the valley, okay? So when I do the transition state, that bond, the bromine is breaking as my bond with my oxygen CH3 is coming in. And then what do we have on here? We have two hydrogens, a hydrogen coming at us and a hydrogen going back. And you do get inversion of stereochemistry. And so there's your transition state at the peak, not the valley. You don't have an intermediate. Intermediate is something that you could get at NMR or some kind of instrument identification. Okay, so now I have questions that students have asked me. I've got about 7 questions here from the wrapper. So we're going to go through these. Okay, so question number 1 from the wrapper. In the following reaction, which is the nucleophile? So we have something like this. All right, so draw your Lewis structures. I told you that the first week. They're going to help you solve these problems. Okay, so there's your Lewis structure. Now, you know, iodide is a great leaving group. So even though it has lone pairs, and we have a delta positive and a delta minus, so we have this dipole. And so this is going to be your electrophile. We have a dipole. Here we have nitrogen with its lone pairs. This is going to be your nucleophile. And so what happens is it comes in backside attack. This is methyl. So your electrophile is classified as a methyl electrophile. And so it's methyl, and here you have a good nucleophile. So this is definitely going to be an SN2 reaction. And what does that product look like? Because you're going to have to be able to draw products. Nitrogen now has a positive charge and the iodine has a negative charge. Okay, so your nucleophile here, the correct answer is the methylamine. Okay, question number 2. What is the major organic product for this reaction? All right, so let's classify our starting material. That carbon bonded to the bromine is bonded to how many carbons? 2. So we have a secondary alkyl halide. So we know that's the gray area. It could be SN1 or SN2. That's your electrophile because we have the dipole here. Oh, we have a weak nucleophile. Okay, so this is definitely going to be an SN1 because we have a weak nucleophile and we have a secondary alkyl halide. That means the rate of the reaction is proportional to your electrophile only. It's not proportional. You can increase the amount of methanol all day long and it's not going to change the rate of reaction. So do not, when you have to draw this mechanism, do not draw two arrows there. You draw one. Step one. Step one in your mechanism, bromine leaves to form the most stable carbocation. So when bromine leaves, you have to form the most stable carbocation. So that's step one in your mechanism. And yes, you will have to draw the mechanism tomorrow. All right, do your carbocation test. Carbocation test. So we're looking at this carbon that's bonded to the carbocation. Do you see it's a secondary? What if it trades places here with a hydrogen? Does a hydride transfer? Maybe a primary. That's not better. What if it traded places here? Okay, well that would be better. Now we don't have a hydrogen, so we can do a methyl shift. The methyls can also move. So this methyl is going to go here, and then you redraw. And so it's this methyl right here. It goes there. And we have this one here. And we trade places here. Now we put the positive there. So now what do we have? This is a tertiary carbocation. Is tertiary better than a secondary? More stable than a secondary? Yes. So this is step one. Now for step two. Your weak nucleophile that's in solution, methanol, can add to the carbocation. So now we got methanol, and methanol is going to add. And this is an sp2 carbon, folks. There's no stereochemistry. It can add, it'll add equally up and equally down. So this is your product, so you'd have to find that product. Question number 3. Which is the starting material for this reaction? All right, so this is that question where OH is a bad leaving group. Oh, I gave you the starting material. Okay, starting material. What is the starting material? And you have this. Okay, this is an allylic halide. So HI is an acid. And so some of these you might need to do each one of these and just do the reaction. Bad leaving group gets protonated. Now remember your allylic can go SN1 or SN2. So here, do backside attack. That's a great leaving group. Water. And there's your product. And would that be an SN1 or SN2? You see how I have 2 electron flow arrows here? And this leaves. Because I have 2, it's in a single step. One step, that's an SN2, folks. Okay, you do get inversion stereochemistry. Question number 4. Here we have an allylic tosylate. And we're adding a thiol ether. And the question is, reaction mechanism. So this here is an SN2. Let me tell you why. This is an allylic tosylate. Now we know allylic and benzylic can either go SN1 or SN2. So you have to look at your nucleophile. Now anytime you see a sodium, make it a positive. Okay, because they do ionic bonding. Do you see you have a negative charge here? That's a strong nucleophile, folks. It's a strong nucleophile. So that means before anything can happen, the fastest, whatever is the fastest wins. This is going to come here, and you're going to have 2 electron flow arrows with 1 step, and you're going to get your product. Okay? All right, the next question, question number 5. Okay, I think that these are mechanisms. Okay, so these are mechanism reactions. We worked one similar. I will do it here. Because you see that you have this light and you have an alkane, this is going to be free radical halogenation. So initiation, the first thing that happens is bromine, and we get 2 bromine radicals. The mechanism is P1, so we take our starting substrate here, and let's put in our hydrogen, because we're going to extract the hydrogen with the bromine radical. I want 3 fishhook arrows here, 1, 2, 3. Folks, I know a lot of books show these electron flow arrows in midair. Because I'm not in the classroom with you every day, I let it go, but I don't like it. Those electrons aren't going to free air, they're going towards a nucleus here. Okay, so they're going towards this hydrogen nucleus. So every electron flow arrow should point to some nuclei. All right. A lot of people were doing their mechanism. They didn't put the HBr. You know, it's wrong. Mechanisms need to have every step to them. Okay. And some people are not doing these half fishhook arrows. So get your points, folks. Okay. The exam is tomorrow and it's going to be worth more points. So now we got to regenerate our bromine. And so we have 3 fishhook arrows again. That's going to go to the bromine. And then these electrons are going to split. One's going to go with the bromine and the other one's going to go with the bromine. And this is how we put our bromine on our molecule, and then we generate another bromine radical. In propagation, on the reactant side, you should have a radical and a non-radical species. And on the production side, you should have a radical and non-radical species. Okay, now you calculate your bond dissociation energies. We do this for homolytic cleavage. So here we have bonds broken. This is going to be a positive delta H. And then we're going to subtract bonds formed. That'll be a negative delta H. That's why we have the negative here. And so we need to list them. So I'll do on the reactant side, I see that this is being broken and this is being broken. So I want these listed. This is an allylic CH. And it's also a BR-BR. And then bonds being formed is the HBr and then this allylic bromine. So we have HBr. Now, I don't think you're going to be able to find the allylic Br carbon on your sheet. So what I've had to do, I just go back to, okay, now we just default to a secondary. And if you did a secondary for the other one, that's fine too. You're allowed to do that as long as you list that. So when I look at my sheet here, I'm going to see that the allylic CH is 372 kilojoules per mole. BRBR is 190. We'll total that up. 2, 9, 10, 3, 4, 5 kilojoules per mole. Subtract. And what's our total here? HBr, 366. These are kilojoules per mole. And then since I don't have the allylic carbon bromine, I'm going to go with just the secondary. And that is 309. So 9 and 6 is 15, 7 and 6 kilojoules per mole. And so what's 675? 502, 3, 7, 1. So negative 173 kilojoules per mole. So it's an exothermic reaction. Question number 6. It's also a mechanism. So we start here. We have a wedge. And we have this in methanol. And we need to predict the product and show this reaction mechanism. Okay, so we have a secondary alkyl halide is our electrophile. This is our electrophile. And our nucleophile is a weak nucleophile because there's no negative charge. So the first thing, step 1, this is going to be an SN1. Leaving group leaves to form the most stable carbocation. So let's do step 1 of that mechanism. You just draw one electron flow arrow, and you draw your carbocation. And then step 2, we're going to have to do our carbocation test. So we have to classify this one. This is a secondary. If we trade places here, that would be a primary. If we trade places here, it would be benzylic and tertiary. Okay, benzylic tertiary. Yeah, benzylic tertiary is more stable. So we're going to draw in our hydrogen here, and then those electrons are going to go here, both of them, and they're going to do this. It's called a hydride shift. It's actually called a 1,2 hydride shift. A lot of times you write that on your paper. Okay, and now we have the carbocation there. You can draw the hydrogen in there. You don't have to. You don't have dashes and wedges. This is an sp2 carbon, so it's flat. Okay, but you see how we had rearrangement. And now our nucleophile, our weak nucleophile, can come in. But in your mechanism, you got to show that first. Right? So then our product and if you do this and you want to show it all, which I think is great, that is, you got to show your formal charges and then another methanol. You have to finish it up though, because I want your major product. The methanol is going to deprotonate that. A lot of times you work this up in a separatory funnel, and this is your product that you would characterize, and it would be a neutral, and that would be an ether. Okay, now, so that is an SN1, and we get rearrangement. Now, what if your nucleophile had been this? Okay, then you would have had SN2. And what would that have been? So let's look at that. What if you would have had this compound with sodium methoxide. Okay, now you have a secondary, and so we're in the gray area. This is going to be an SN2 because we have a strong nucleophile. Okay, so now we're just going to have 2 electron flow arrows. They're going to go here from the oxygen to backside attack, and iodide leaves. And now I draw the product. I have to show my stereochemistry, folks. This carbon wasn't changed. You see how now I have backside attack, so I have inversion of stereochemistry. So notice there's no stereochemistry in the SN1 reaction. We had rearrangement, and here in the SN2 we have inversion of stereochemistry. So I will put on your exams, show stereochemistry when appropriate. I expect you to know that, okay? That's usually worth a point. So sometimes on these multiple choice questions, though, which are 6 points apiece, that's the difference between a right and wrong, and that's a 0 versus 6 points. So pay attention. Okay, another student asked, still having trouble understanding the dipole moment versus no dipole moment. So I picked this example to show that, and we're going to see this again in chapter 7, so it was a good question. Okay, so which one of these have a 0 dipole? All right, and the answer is this one here. So let's look. If you drew in your dipole, it goes towards fluorine, and this goes towards bromine and bromine, okay? And then if you add them all up, okay, this is less than this. So overall molecule would have a little bit of a dipole going to the left here. Okay, so we'd say that's greater than 0D. Might not be much, but it would pull a little bit to the left here, because if you put in the numbers, fluorine is 4.0. You could look at the chart. I mean, you're looking at probably like a 2.7 or something here with bromine. Now here, because of the geometry, this is going to pull here, your bigger ones, and this is going to pull here. We really don't show the dipole between a carbon and a hydrogen, and we say that that's equal. Okay, so if this equally pulls from the top and equally pulls from the bottom, they're going to cancel each other out. And therefore, that net will be a 0 dipole. So anytime you have symmetry, like carbon tetrachloride, that would also be a net 0 dipole, because you have equal pull by each one of these, and they have symmetry. So you look for symmetry in the molecule, and then that would be a 0 dipole. All right, I think that sums up all the questions that I have received, and so hopefully this Q&A session was helpful, and you just keep working it and do really well tomorrow. The exam will not stay open on Friday. I am actually going out of town. I'm going camping, and I need to get away from my computer. So I am going to grade your exams Thursday night, and so if I have those exams, I will post them on Friday, and that will let you know whether you want to stay in the course or if you need to withdraw. I think Friday's the last day, and then I will just try to check emails when I can. But you might have to, if you do not hit this deadline, you might not get your exam posted again until Monday or Tuesday. So if you submit all your exam materials on time, which is Thursday by 5, you will have that graded and everything before I leave town on Friday. Okay, have a good evening.